everybody! Today we are going to be talking about calorimetry, so kind of the lab that we did to start our unit off. Part of calorimetry is that there are heat changes happening. So before we actually get into the specifics and the calculations of calorimetry, we're going to talk about describing those heat changes. So the first part is thinking about the universe in two parts. One of the parts is the system and the other is the surroundings. Okay, so the system is basically whatever we are studying. Okay, so specific part of the universe that contains that reaction or process that we're studying. So whatever we're studying is going to be the system. The example in our calorimetry lab that we did is the metal sample that we had. Okay, so that was the thing that we are studying. We're seeing how heat is changing, especially with that metal sample. The surroundings, on the other hand, is everything else. Once you know what the system is, the surroundings is everything else that has an effect on that system. Okay, so in the calorimetry lab, we had the metal, and it was in water, right, in the calorimeter, in that styrofoam cup. So the water is a surrounding. The styrofoam cup itself is a surrounding. And then the air is also affecting it. So the air is also a surrounding there.
So we're going to talk more about systems and surroundings and the exchange of energy between those, as we saw the other day, in the form of heat. But we're going to really first need to cover the first law of thermodynamics, which is also known as the law of conservation of energy. You guys probably learned about this in middle school, but basically it is very similar to the law of conservation of mass in that energy is neither created nor destroyed. So in a chemical or physical process, energy is completely conserved. It's just transferred. It's not created or destroyed. So that transfer of energy we can measure and we do problem solving with, and you're going to see that in a few minutes. But it's basically transferred between the system and the surroundings, so in one direction or another. And that happens until the final temperature is equal for both of those. So our T final is always going to be the same because of that transfer of energy in the form of heat. Now there's two different ways that this could go. The system could be transferring energy to the surrounding, or the surroundings could be transferring that heat to the system. So if the system is losing or giving off energy, heat, in the form of heat, we are going to have a negative Q value, and that is an exothermic reaction. Our system is losing heat.
Think of like exoskeleton from biology. It's on the outside, so it's given off.
An endothermic reaction, on the other hand, is when a system is gaining heat or absorbing it, and that gives us a positive Q value. Remember when we say loses and gains, it's not like this just energy poofs from nowhere. It is either existing in the system or the surroundings, and there's this perfect exchange of energy. And that's why we can use, that's what we use to do our calculations. So just an example to talk about these four vocabulary words right now. We have concrete being heated by the sun. So our system is,
what are we studying here? We're studying the concrete. So the concrete is going to be our system. Then our surroundings is everything besides the concrete. So we would have the sun. That's something that is surrounding the concrete. And also, hopefully you notice the atmosphere or the air is going to be surrounding the concrete. So those are the surroundings for our system of the concrete.
And often when we are losing energy or losing heat, it's always being lost to the atmosphere. The atmosphere is always absorbing all of our heat all the time.
Yeah. But within our universe, we're not losing energy.
Yeah.
That's where it's going back and forth.
It's going somewhere.
So is this an endo or an exothermic reaction? Our system is the concrete. Is the concrete absorbing heat or is it giving off heat? Right? Hopefully you realize it's absorbing heat from the sun. Okay? So if it's gaining or absorbing heat, this is an endothermic reaction. And our Q, is it going to be positive or negative? Should be a positive Q value, positive value for heat.
Okay. So calorimetry is what our lab, basically our lab the other day that we did was a calorimetry lab. That was weird. And it is a process that measures heat changes for chemical reactions and physical processes, and we use Q equals MCAT, which we talked about in the last video and practiced in class, and a new equation that is representing our first law of thermodynamics, which is Q system plus Q surroundings is going to be equal to 0 because we're neither gaining or losing any energy. It's not being created nor destroyed. So this value will always cancel out this or vice versa. It's going to be equal to 0. We rearrange that to say Q system is equal to negative Q surroundings, which you're going to see down here. So thank you. So our problem-solving steps for solving our calorimetry problems are always going to be these three. First, we calculate the heat gained by water. Now you'll see, just similar to our gas laws unit, you need to use all of our mass value, our specific heat, and our change in temperature for water when we are doing this. And over there, when we are calculating the specific heat of the metal, we are using all of our values for metal. So it is important to write down all of your variables. So first you solve for the heat gained by water, and that is going to be QH2O equals MCAT. So we use the mass of water times the specific heat of water, which is 4.184 joules per gram degree Celsius, times delta T. Once you solve for that, you calculate the heat lost by the metal using the first law of thermodynamics, which we just talked about right here. Q water plus Q metal is going to be equal to 0. If I rearrange that formula, my Q metal is equal to my negative QH. The heat lost by my metal is going to be equal to the negative value of the heat gained by my water sample, okay? And it is negative because the metal is transferring that energy from itself to the surrounding water. And then we calculate the specific heat of the metal, again using Q equals MCAT, and we do that again with, make sure you use the mass of the sample, make sure you use the change in temperature of the metal sample, and you are isolating for that specific heat. This is what we're going to do in our lab write-up. And so you'll find that the specific heat of the metal is going to be equal to the Q metal divided by the mass of the metal times the change in temperature. And that change in temperature is going to be negative, and so will this value will also be negative, so that's going to cancel out. Your specific heat should always be positive.
All right. We're going to do one example because calorimetry problems are pretty long. You'll see this in the lab as well. Our example says, and I've already put the variables in a different color, in the pink color, so hopefully you can see that. Calculate the specific heat of a metal if a 24.7 gram sample of an unknown metal at 92 degrees Celsius causes a 42 gram sample of water initially at 20 degrees Celsius to rise in temperature to 22.5 degrees Celsius, okay? So we need to start with step 1, which is calculating the Q of water, the heat of water. Okay, we're going to use our equation down below, Q equals MCAT, and remember we're going to plug in all the variables for the water, so we need to write them down. So, we already know that the mass of the metal sample right here is 42 grams, and I wrote in the specific heat of water because this specific heat for water is always the same for water, 4.184 joules over grams degrees C, okay, always for water. Now, we need our initial and final temperatures so that we can calculate this delta T. So we're looking for our initial temperature. So let's see. Sample of water is initially at 20 degrees C, and it rises in temperature to 22.5 degrees C. Okay? So when we calculate our TF minus TI, we have 22.5 minus 20, and that's going to give us 2.5 degrees Celsius. Okay? Now, when we actually go to using sig figs, make sure you're looking at the original numbers given in the problem, not this 2.5 for sig figs, because the original numbers we have each have 3 sig figs, okay? So we're going to plug this in. Q equals MCAT, so we have 42 grams times 4.184 joules over grams degrees C times our change in temperature, which is 2.5 positive degrees C, okay? So our Q of water, when we do the math, is 439. And we can see that our unit is going to be joules because Celsius cancels and grams cancels. So we're left with joules. All right? Now, easy enough, right? Positive 439 joules. Okay? Easy enough. We've already done that. We've calculated specific heat already. Step 2 is a little different than we've done before, but not hard. We're going to calculate the Q of the metal. We know that Q of metal is equal to negative Q of water. So the Q of metal is just negative 439 joules, okay? Here's our Q of water, negative Q of water, so negative 439. Easy enough, right?
Because there's that perfect transfer of energy from our metal to the water.
Okay, so all we did here, plugged this in there. Now we're going to take this and we're going to plug it in for our Q of metal. That did not work well. We're going to plug it in right there. Okay, so we need our variables for the metal now. Heat of water, heat of metal. Now we're going for the specific heat of metal. Okay, so our mass
is 24.7 grams of an unknown metal. Our initial temperature is 92.0 degrees Celsius.
And I'm going to pause this right here because I put a note up here that I meant to point out. Remember that when we add the metal to the calorimeter, we are taking the temperature. Remember we had you stir and take the temperature until it reached its highest point. That highest point was the point at which the metal and the water were the same temperature. Okay? So you're stirring and stirring and stirring until they come to equilibrium. That means your final temperature of the water should be equal to the final temperature of the metal. Okay? So if the water rises to 22.5, and that's the final temperature, then that's also the final temperature of the metal. Okay? TF, 22.5. TF, 22.5. They need to be the same. Okay? Now we can do our change in temperature. TF minus TI, and I did not leave a lot of room there, is equal to negative 69.5 degrees Celsius. Okay, so TF, 92. No. TF, sorry, 22.5 minus 92. We get a negative. All right, so we're going to use Q equals MCAT again, this time for the metal. But remember, we need to rearrange the equation. So to get C all by itself, we need to divide by M delta T. Delta T crosses off, M crosses off. So we get C is equal to Q over M delta T, which is what I have here.
So we are going to take the Q metal, which we solved for right here, negative 439 joules, divided by the mass, which is 24.7 grams, times negative 69.5 degrees Celsius. You'll see that now we had our two negative values, which makes a positive, and we end up with
0.256. And notice our units don't cross out. We have joules over grams times degrees C.
Which is what we want for our heat, specific heat. So that's the specific heat of the water. And the specific heat, of the metal. The specific heat of the metal is kind of like density. It helps us identify substances often.
So we could look up the values of specific heats for different metals and actually identify, oh, this must be whatever metal. We really should have looked that up before this.
We'll tell you in class.
We'll talk about it in class.